All right, so I'm going to talk to you about some research we've been doing for the last couple of years. Everything started with this event that will cover the beginning of my talk. We call it the Icarus event. It's right now probably the most extreme example of magnified event. We estimated somewhere between 2,000 and 3,000. That's the magnification. And it's what we saw in this case was a star at redshift 1.5, a single star at redshift 1.5. Today, this star is by far the farthest we know. The previous record holder was like 200 times closer than this one. So that will cover a little bit the beginning of my topic. Then I will go into what was kind of like the evolution for us, and the motivation or the common link between the two. It's something that is relative to this conference. In particular, my main interest is what can we learn from dark matter, about dark matter. And basically, this topic will be how can we say something about dark matter from these kind of events. This is, again, one of the motivations. Most of you know about LIGO. This is the kind of masses that LIGO are finding, of the order of 10 to 30 solar masses. And one of the candidates even discussed on the LIGO papers for this type of black holes is primordial black holes. It's an old idea. There's nothing new here. There are some constraints. There's been a lot of work in the past trying to constrain what is the fraction of dark matter that can be in the form of primordial black holes. And these are the constraints you see. And this is the range of LIGO masses, which in theory, you can have up to a few percent or 10% or so of the dark matter in the shape or in the form of primordial black holes. And that could explain, for instance, why LIGO is finding the black holes that it's finding. So can we constrain this with this type of extremely highly magnified events? Again, this is part of the motivation. These are the masses of the black holes we knew from our own galaxy before LIGO. These are all coming from measurements of X-ray binaries. And here you see the masses found by LIGO. Even to the eye, you see there is some discrepancy here. Either LIGO and the X-ray binaries are seen to different types of populations, or there is something going on. Is our galaxy special? Why don't we see those black holes there? What's going on? So what can we say about this using extremely magnified events? This is that Icarus event I told you at the beginning. Icarus appeared in 2016. This is an older image from 2011. In this point, you barely see anything. If you take a deeper exposure, you would see a little dot there. It's not shown in this picture, but you have to believe me, it was there. But in 2016, we saw that little dot going up in flux by quite a bit. In fact, it increases the flux by almost 2 magnitudes. Then a few weeks after, it went down again. And just to put it in context, this is the same dot, right? This is the Icarus star. And what you see here, these lines, it's where we believe the critical curves of this cluster are. Critical curves are the regions in a gravitational lens where the magnification can diverge. It can be many thousands of times. And the dashed lines is the range or the uncertainty of where the critical curve may be. So we don't know exactly where the critical curve is, but what we know for sure is that this object is extremely close to the critical curve. When we saw this object, what we thought it was going on is that the critical curve was going right in between. Because if the situation was like this, we should see we should see two images, which we didn't see. So at first we thought the critical curve was going right in between, but then a few months after we saw another event there. And then we say, voila, the critical curve goes in between. And then this point disappeared a couple of weeks after. The mystery here is why didn't we see this point before, right? So this is where microlensing comes in. What happens when you look at the magnification near a critical curve? This is the classic picture. This is a small portion of the lens plane in a galaxy cluster, small field of view, and then the critical curves are at a straight line, right? So in the classic picture, if you go to textbooks or papers or so on, you will see a description of critical curves as smooth, single lines like this. That's what we learn when we go to lectures of lensing, for instance. This is totally unrealistic. This is not the case. As a consequence of this work, what we found is that in a realistic scenario, what you have is the critical curve breaking up into very large number of micro critical curves, each one surrounding a microlens. And why is this? This is because in every critical curve, you are always going to have some microlenses. It could be stars from the galaxy, it could be stars or remnants from the intracluster medium, it could be anything, but you'll never find this situation where you don't have any microlens at all. This one in the bottom, where f is equal to 1, this f means the fraction of microlenses that we know they are there. And we can constrain how many microlenses are here by looking at the intracluster light. So f equals 1 means this is all the microlenses we know are there, right? So this is what you expect. So how can we use this to interpret what we saw? This is again the same plot I showed you earlier. This is the Icarus event. This is the other event. That's Icarus. One funny thing about lensing is that when you are considering lensing on very small scales, in particular microlensing, images on either side of the critical curve don't behave the same. This is another difference with standard lensing when you're dealing with galaxies and images from galaxies. Normally, when you have a pair of images around a critical curve, they are more or less similar, almost identical. In this case, the difference can be very substantial. Why? This is what the source is in. These are what we call the caustics, is the magnification in the source plane, not in the image or the lens plane, on this side of the critical curve. On the other side of the critical curve, the caustics are very different. You see here regions of very low magnification, these dark areas, which are not present there. So when a star is moving in this field, it will spend a lot of time in these dark regions and little time on these bright spots. So most of the time the star will be invisible because it has very small magnification, and occasionally it will cross one of these caustics and it will go up in flux. While in this case, the star, even if it's here, still has significant magnification. It could be magnification here, the minimum can be like 600 or so, and the maximum can be like 5,000. If you build light curves, if you assume a star is moving across this field, on this part of the field, it would do something similar to the red curve here. There would be extended periods lasting up to 10 years where you don't see the star, the magnification is very, very low, and then there are some peaks. While on the other side, you have to look at the blue curve. There is always a minimum magnification of the order of 600, and occasionally you have peaks up to a few thousand. When you compare that with the data are the dots here, and the curves are basically two models, right? So the models which are built from what we know about the microlenses, and again, the microlenses are constrained by the amount of light we see in that part of the cluster, those microlenses are enough to explain what we saw. Now, can we say something about primordial black holes here? And the truth is that, yes, we can say a lot. If you start populating that lens plane with microlenses, for instance, with primordial black holes, with masses similar to the ones that are being found by LIGO, you would see light curves which are like this. Much more noisy with many more peaks. And this picture is inconsistent with what we saw here. There are some peaks, but there are, in this period of time, it's relatively smooth. So this cannot be. How low can we go? How much can we constrain the amount of primordial black holes? Right now, the limit is at the level of 3%, more or less. We can do better when we get more data. But this is very promising. Just with one star, monitoring that star, we can put very strong constraints on the amount of primordial black holes. Can we do better in the future? Yeah, I mean, of course. This star, even though it's very promising and it's the first one, is not ideal because it has a lot of microlensing from the stars, and that's noise. Ideally, you would want a situation like this where you don't have microlenses or few microlenses, so the distortion is relatively small. That's going to be hard to find, but it's a question of time. We believe with the James Webb Space Telescope, this new type of science will be much more common in the next years. Again, this is what you would expect in the classic picture, just magnification grows as you approach the caustic, and then it goes to 0. And this is what you get in reality. This is a zoom, and this is a better picture. The classic view is not valid, ever. You never will find a situation where you will find this kind of situation. This orientation is not accidental. We made it on purpose. It gives you the impression that you're kind of climbing a hill, and a hill has two sides, right? The side you see and the side you don't see. Those two sides represent these two parities, right? I'm going to go a bit faster over this part. So one of the things that microlensing do, for instance, it forbids very, very extreme magnifications. For instance, magnifications above 10,000 or 20,000 will probably never happen, which in theory, they were possible before if you ignore the role of microlenses. But microlenses being near the critical curves will prevent that from happening. Of course, energy needs to be conserved, so that lack of extreme magnification gets compensated. So you get a boost at intermediate magnifications. And magnifications of order 1,000 or 2,000, you are about twice more likely to see events when you have microlensing. And at low magnifications, there is some significant changes too. Another interesting thing is that when you are approaching the critical curve, no matter how many microlenses you have, at some point, you are going to not be able to distinguish one side from the other side of the critical curve. And the width of this region is proportional to the surface mass density of microlenses you have. In other words, if you start putting primordial black holes there, this region is going to be wider than if you don't have the microlenses. That's another way of testing or checking for primordial black holes that hasn't been used yet. So that's the first part of my talk. I'm going to go really quick over the second part. This is still related to microlensing, but first is more related to standard lensing. So this work we did a year ago, it got some attention. The motivation is the same I showed you earlier. Why aren't we seeing these massive objects in our galaxy? And we made this assumption, or hypothesis, if you want, where we claim that the low frequency events observed by LIGO, the ones that are more extreme in terms of mass, are not really that massive. They are not black holes with masses of 20, 30, but instead they are black holes with masses of 10 or 15 that are strongly lensed. And for those of you that have followed the story of Herschel, the brighter sources it found were all strongly lensed. So we think a similar mechanism is going on with the gravitational waves. If you take a gravitational wave and you lens it, and then you ignore lensing, which is what LIGO is doing by default, they assume that no gravitational wave is being lensed, then you get a bias on the mass. You infer that the mass is higher and the redshift is smaller. These are two examples of a gravitational wave at redshift 0.09, like the first one that was detected, and another one at redshift 1, but magnified by a factor 250. And you see the strain is identical. You couldn't tell the difference. I'm going to skip this. So what's the probability of having these events? You can compute the optical depth of lensing. You find for magnifications of order 100 is of the order of a few times 10 to the 7, sorry. You can do a back of the envelope calculation with this number. If the probability is 3 times 10 to the minus 7, and I take a redshift slice between redshift point 1.9 and 2.1, I have this volume. I assume a rate this high, and then this is all the rates you have, and one of those will be lensed with a magnification above 100. And that's the one we claim LIGO is in. Of course, for all of this to work, you need a high rate, right? These are the models we were using. This is the high rate I was talking about, the mass functions for the black holes. And I want you to look at this solid line. This is our winner model, and I'll show you why later. Right? And this is just a Gaussian and another log normal. And this high rate that I always thought it was a bit crazy, it's a bit high, and that's probably our Achilles, whatever the expression is, I don't remember, heel or something like that. I found out recently in one of the LIGO papers that the best model they find for constraining the evolution of the rate is consistent within basically 2 sigma with this model. So that's very encouraging. Just want you to look at this plot. So basically, if you take these models here, the rate and the mass function, this is what you would expect if there is no lensing. You would expect a lot of events distributed in this way. These are the 6 events that were published last year. Now there is more, and the new ones are kind of there. But there is no evidence for any of these events on the data. If you now allow for lensing with this high rate and high redshift, this is what you expect. These color dots are the events you expect, and these are the ones that are not being lensed. And the agreement is better with the data. So this is very encouraging. This would be the redshifts and the real masses of the events. And these are the ones that you interpret here in the detector if you ignore that lensing is taking place. We made a prediction a year ago. This would be the mass function that you would find, a peak for the lens events, and another peak for the not lens events. You look at the new data that came out at the end of November, and this is what you find. A peak, exactly where we predicted the lensing peak to be, and a peak, a low masses that would correspond to the non-lens events. This model is the model for the events that are not being lensed. For this to work, you need a model that is like this one, but it goes a bit lower, even at low redshift, okay? And then you can bring this peak down to that level, and you would reproduce something like this. So this is all very nice, but how can you test, how can you prove that a gravitational wave is being lensed? This is where microlensing comes in again. Gravitational waves have a very long wavelength, many, many kilometers. So it's easy to imagine that if you have microlensing, where the time delay could be of the order of milliseconds, you can have 2 gravitational waves arriving with a difference of milliseconds, and then they would interfere. They will give you an interference pattern. This interference pattern, to the best of my knowledge, cannot be reproduced by playing with the parameters of the binary black holes. So this is just one example. This is going to be out in a week or so. These are just stellar masses. This is from a realistic simulation. This mass is of the order of 11 solar masses. This is 2 solar masses. It's like 0.5 or so. And this is just one example of a microlensing event, not by one star or 2, but by the whole conglomerate of stars from the galaxy or the intercluster medium. It's just a zoom of this region. And this is the kind of interference pattern you would expect. This is the LIGO frequencies. So basically what you expect is in the LIGO frequencies, the strain to weaken at these frequencies. This is the amplification or the magnification. It weakens by some significant percentage around, what is this, 300 or 400? I don't see it really well. Hertz. And then quickly it increases again. Its amplitude. And this is a very distinctive pattern. Of course, it depends on the type of microlenses you have there, but this is, we're producing a lot of these patterns. This is something that could be observed with even today's LIGO signals. They are not looking for this yet, but we hope they will. And I'm out of time. I'm going to conclude here just with a few remarks. If there is one thing you should take home, it's the idea that these extremely magnified events give you a lot of information, not only of the distant object, but at least for me, more interestingly, what is going on in the lens plane. All these small perturbations you have in the lens plane get also magnified when you're seeing an event that is magnified by an order of 1,000 or 2,000. So you can learn about the small structure of mass, particular dark matter. If dark matter is clamped on small scales, you can learn about it by studying these events. Thank you.
So questions?
To make a comment on your last point about LIGO having not searched for microlensing effects, which is actually incorrect. Some of us has done a search for evidence of microlensing in the LIGO events by a full Bayesian analysis, assuming a point lens model. And so far, we have not seen any significant evidence of microlensing effects in LIGO events. And the comment on the explanation of lensing to explain the high mass events, it requires very strongly on your assumption of the mass function. Mm-hmm. So even if you, a lot of people argue that having higher mass black holes is much more natural than to evoke the special conditions on the merger rate peaking at redshift of 2, as well as this very narrow mass function of black holes also. And finally, on your comment, again, we have looked at the evidence of multiple imaged lenses in the LIGO events and using a more rigorous statistical analysis. And we do not see any evidence of more than 1.5 sigma to support the evidence. And if you look at the overlaps of the posterior distributions of LIGO events in many other parameters, they are non-overlapping. So we do not think that the evidence is strong enough to claim lensing.
One question for you. When you say you look for microlensing events, are you assuming single isolated microlenses? Yes. That's totally unrealistic. That doesn't exist in nature. Every microlens is embedded in a potential, a galaxy or the cluster. The properties of microlensing change quite a bit when you have a microlens in a potential. Using isolated microlenses, it's totally unrealistic. That's going nowhere.
Okay, so there was at least one search for assuming a simple lens model, which does not show any evidence of microlensing effects.
All right.